Okay, this is part 2 of our timber beam design problem. We're looking at problem 1629 from the text, and it's a joist problem. So we had to find the distributed load, the little w, in terms of, I found it in terms of pounds per inch. I used that then to find the maximum moment. And using that maximum moment and the allowable bending stress for hem fir, I found the section modulus that was required. Then we double checked, just to be thorough, the additional moment caused by the self weight and how much additional section modulus was going to be required due to that self weight. Turns out it was not very much, less than 1 inch to the third. So our original requirement of 15 got bumped up to 15.8 or 15.9 if we rounded up, which is still less than what we are providing with the 2x10, which has a section modulus of 21.4. So as far as bending stress is concerned, our 2x10 is going to be adequate. I don't believe the textbook gave us a deflection limit to check, but it's not a bad thing to do, and especially since you'll be needing to do that on the test, I'm going to go ahead and work that out here in this video. So let's just say that our deflection limit was given as L over 360, the span length divided by 360. Then that would correspond to, if we scroll back up here to the problem statement, we had a span of 12 feet, or converted to inches is 144 inches. So if I take my 144 inches divided by 360, that is equal to 0.4 inches. So we don't want our beam to deflect any more than that. What is our actual deflection? Well, all the loads in this case come from a simply supported beam and a uniformly distributed load like we have here. So the equation for that is 5WL to the fourth over 384 EI. Now I just happen to have that memorized because this is the most common type of support and loading condition. But if you don't have it memorized, it can be found in Appendix H in your book, these equations for maximum moment and maximum deflection. So we're looking at 5 times a uniformly distributed load of, what was that? We calculated that earlier and found that it was 5.78. Plus we had a self-weight. We should include the self-weight here. And that is 3.85 pounds per foot. If I convert that, 3.85 pounds per foot multiplied by, for every 1 foot, there are 12 inches. So I'm going to be dividing 3.85 by 12, and that's equal to 0.32 pounds per inch. So our total distributed load, W, would be the 5.78 plus the 0.32. So the total distributed load is 6.1 pounds per inch. That's our total distributed load, including the externally applied loads and the self-weight. So 6.1 pounds per inch. The length is 144 inches to the fourth divided by 384. The modulus of elasticity. I know we do a lot of steel design problems, and so you might just think, oh, modulus of elasticity is 30,000 KSI. But this isn't a steel problem. This is a timber problem, specifically hem fir. So we looked that up earlier. The modulus of elasticity of hem fir is 1400 psi. So down here goes 1400 psi. And the moment of inertia about the x-axis, we also looked that up earlier, 98.9. Okay, and then we put that into our calculator. Let's see what we get. I am getting 246.7. Obviously, that's not right. Okay, so I considered going back and editing this video because obviously I made a mistake. But I think it actually is a good learning moment, a good teachable moment here. And so I went back and looked and found what my problem was. And it's a unit problem. And so this should be 14, I'm screwing it up again, 1400 KSI. So I would have to add 3 more zeros there. So it's 1.4 million PSI. So this value is not correct. It should be 1.4 million PSI. So I went back and checked in Appendix F. This 1400, I didn't look closely here. All of these allowable stresses are in PSI. I just assumed that was PSI also. I didn't look up at the top of the chart to see that's actually KSI. So you can learn from my mistake, hopefully. So up here, this PSI was wrong. This should be 1400 KSI, which is 1.4 million PSI. So that's where my mistake came from. And I always encourage people to think about their answers. Think, does that make sense? Does it make sense that this beam, which has adequate strength with respect to bending stress, would deflect in the middle 246.7 inches? No, of course not. That doesn't make any sense at all. It should be 1, 2, 3, move that decimal place over because I was off by a factor of 1,000. 0.2467 inches is the actual deflection. If I compare that to the maximum allowable deflection set up by my L over 360 limitation, that is less than 0.4 inches, and so therefore it is okay. So make sure you pay attention to the units, even the units that you look up in the textbook, and make sure you write them down correctly. So that was my mistake there. So I fixed it, and what's most important is I recognized it. Then I fixed it, and it turns out this 2x10 is good for deflection. And then the last thing we need to check is shear. So we have a rectangular cross-section here. When we're dealing with timber, we usually do deal with rectangles. And so the shear resistance of a rectangle is, well, let's see here. Our formula is actually not set up to calculate shear strength, but rather the required shear area. The area required is 3/2 or 1.5 times the shear force that the beam is subjected to, divided by the allowable shear stress. So the amount of shear our beam is subjected to is basically just the total load of the self-weight and the externally applied load divided by 2. We've got a simply supported beam, we've got a uniformly distributed load. So if we cut that right in half, half of this load is going to one side and half to the other. If we think of what the shear diagram looks like, it's going to look like that. So the maximum shear takes place at the support. So what would that be? Well, our scroll back up here a little bit. Our distributed load is 6.1 pounds per inch. So we've got 6.1 pounds per inch multiplied by 144 inches is the span of the beam. That's 144 inches. And then divide that by 2. That's equal to 439.2, or I could even just round that up to 440 pounds is the maximum shear force. So the area we're going to need is 1.5 times that shear force of 440 pounds divided by the allowable shear stress with respect to shear. The allowable shear stress, not the bending stress, not B, but V for shear. That allowable stress was 150 psi. So 150 psi goes in there, and then we calculate this value and get 4.4 square inches. So this is the area we need. Does our 2x10 provide adequate area? And it turns out a 2x10 has an area of 13.9 square inches. So this is much less than the actual area that's provided. So as usual, shear is not a concern. Shear is okay. So that means our 2x10 is okay. It has a section modulus big enough to keep the bending stress below the allowable bending stress for hem fur. The shear stress is going to be less than the allowable shear stress. And I even threw in the added limitation on deflection and found that it satisfies that requirement as well. So it checks all 3 boxes, and so we can conclude that we are going to use a 2x10 is the size we need. And that is timber beam design.